Welcome again to my YouTube channel and welcome to another episode of Visuals with Man. Before we dive into the mathematics, let us look at 3 core goals for this session. Please pause the video and go through each objective carefully. Let's walk through the historical timeline of complex dynamics, starting from Fatou and Julia's foundational work in 1918, through Mandelbrot's coining of the term fractal and Brooks and Matilski's work in 1978, up to Mandelbrot's first visualization at IBM on March 1, 1980. Now let's define a fractal. Its Latin root is fractus, which means fragmented and broken. It is a geometrically torn object exhibiting self-similarity across infinite scales, where each part is approximately a smaller copy of the whole. Please feel free to go through the master worksheet. The link is in the description below, where we have abundant Facebook and YouTube resources serving as an introduction to the Mandelbrot set. Notice how the Mandelbrot set is not drawn directly. It gradually emerges. As iteration counts increase, the white region of surviving parameters refine, while the red escaping regions eliminate, illustrating how extraordinary complexity arises from a simple rule. Alright, so finally let us watch a live demonstration in our companion video, this one, showing how one single pixel orbit evolves and remains bounded to belong to a set. Let's have the core iterative mechanics of the Mandelbrot set. Let's have a look at the recurrence relation, introducing the fundamental equation. Z sub n plus 1 is equal to z sub n squared plus c, with the starting initial condition of c sub 0 equal to 0, which is the origin. And next we examine complex parameters, where each pixel coordinate on the complex plane serves as a parameter, and we have this notation here, where c stands for complex number, and each complex number has 2 components. A is for the real part, and B is for the imaginary part. Finally, let's observe orbits and actions, visualizing how the sequence of iterates z sub 0, z sub 1, z sub 2 behaves over time. Alright, so our next iteration step here is iteration 10. So to compute for the next iteration, that's iteration 10, we need to square the previous iteration, okay, which is z sub 9, and this is the value here. And in squaring it, we use the binomial expansion a plus b squared is equal to a squared positive 2ab positive b squared. Okay, and then after getting the value, we add c by combining the real terms and the imaginary terms, and we got this one. And finally, we compute for the modulus using the Pythagorean theorem. Z modulus is equal to the square root of x squared plus y squared. So for this case, the modulus of z sub 10 is 0.614243, which is less than 2, so this remains bounded. So let's go through this video clip here to see which pixels remains bounded and which ones escape to infinity. Again, for our first example, we have this parameter. C is equal to negative 0.20, positive 0.60i. Okay, and computing for the modulus of iteration 20, or the modulus of z sub 20, we have 0.38189696, which is less than 2, so it remains bounded. Okay, and this never diverges to infinity. Because its orbit remains bounded and never diverges to infinity even after many steps or many iterations, then we can say that this parameter corresponds to a pixel that is part of the Mandelbrot set. Now for our second example, so we set C is equal to negative 0.75, positive 0.10i, and we compute for the modulus of iteration 20. So that is modulus of z sub 20 is equal to 0.514484. Okay, and that is under the threshold of 2. And since the orbit of this parameter here remains bounded and never diverges to infinity, then we can say that this parameter as a pixel is part of the Mandelbrot set. Here's an example of a parameter that escapes to infinity. So we have parameter c is equal to positive 0.50, positive 0.50i. And yes, at iteration 4, okay, the modulus is this one. So we have the modulus of z sub 4 is equal to 1.705918. Okay, so at this time, it's still bounded. And yet, let's check out the next iteration, okay? However, the next step, iteration 5, we have the modulus of z sub 5 equals to 3.549354. which crosses our threshold of 2. So we can say that with this parameter, the orbit escapes to infinity. Consequently, this parameter equals to positive 0.50, positive 0.50i is not part of the Mandelbrot set. Right, so we see the same narrative for the remaining pixels. Okay, we have c is equal to 1 and c is equal to negative 1.80, positive 0.20i. Okay, the modulus of those two parameters crosses the threshold. So we can say that their orbit escapes to infinity. So those two parameters as pixels are not part of the Mandelbrot set. Now let's have a look at another video that I created. This is to observe escaping orbits. So we'll be starting from the origin and then the external point. So we have the external point here, which is outside the Mandelbrot set. So let's play this one. Alright, so we can see clearly here that the orbit escapes to infinity as its diverging path head outward. Right? Observe again. Again, we have a theorem about the magic threshold, which is 2. So when the modulus of the current threshold is already greater than 2, then the modulus of the next iterate will also be greater than 2. Now we're going to define a count or escape count. So this is exactly the exact number of iterations required to cross a threshold. And we can have computer programs for its color coding. So dark ones, the high iteration slow escapes, then we have yellow and red for low iterations immediate escape. So thank you for watching, and I will see you in the next part of this video series celebrating the Mandelbrot set. Bye for now!